Am I audible?
Yes, sir.
Let's wait for a few more minutes.
Okay, sir. Sir, week 6 we had done, we have to start from week 7.
What?
Sir, week 6 we had done in last class, we have to start from week 7.
Oh, okay then. Then wait a minute. I'll download week 7 content. Should I wait for a few more minutes? Just should I wait
Yeah,
for
no
like
problem.
5 more minutes?
Yes.
Okay, I think nobody else is coming. Your friends are not joining. Hello, Dhruv.
I don't know about others, sir.
Okay, then I'll just start. I'll just teach you. Okay. So week 7, I'll start from the beginning, right? Correct.
Yes, sir. Yes.
So in week 7, the topic is called frequency response because what we are going to see is, yeah, hello. We are starting a new topic today called frequency response. So in this week, what we are going to be asking is this question. If I give the system a sinusoidal input and then observe a steady state response, then what will happen to it? That is what we are going to see. So it turns out for a linear time invariant system, if you give a sinusoidal input of frequency omega, the output will also be a sinusoidal output at the same frequency omega. The only things that can change are the magnitude and phase. So the output sinusoid may be of a higher magnitude or a lower magnitude or the same magnitude as the input sinusoid, and the phase of the output sinusoid compared to the input sinusoid can be out of phase or in phase. There can be a phase difference. So that is what we are going to analyze. What kind of systems will cause what kind of magnitude change and phase change for a sinusoidal input at a given frequency. Okay. So, for example, take the system 1 by s plus 1 transfer function. If you give the sinusoidal input, after some time, the red part is a transient part, forget that. After some time, what you see is the system settles down to the same sinusoidal output or the same frequency, but the magnitude is not 1, right? What's the magnitude of the input here or output here? For sine 10t, what is the magnitude of the output at the blue when it is the blue stage?
0.1.
Yeah, so
Point
it is
one.
reduced, right?
Sir, just 1 sec to confirm. Today we'll cover the entire week 7, is it?
Let's see how far we can go. Depends on you. Depends on how far you can take. Ask me a
I'll
lot of questions and
consider
interrupt me.
two is just on our heads. We've already, I mean, for the most part, I believe most of us have already done this week. So I mean, even if you brush through the concepts as a revision, it would work. I'm not sure about others, so they can certainly pitch in and correct me if I'm wrong. But I think we've covered this part. I mean, on our ends.
I mean, as the previous instructor taught you in a live session, or you have watched the videos.
Watch the videos, done the PHGA.
How about the other Sanket?
And I
Hello.
think Dhruv and Kajal as well.
Why are they not answering? Dhruv, Kajal?
Yes, sir. I have watched half of the videos almost.
Hmm?
Sir, I have watched half of the content
Till when?
till Nyquist stability criteria.
Till?
Till
Ma-
Nyquist stability.
Okay. Till where here? This you watched?
Yes, sir. First three videos I
Okay.
watched.
First,
First three lectures.
first three examples. Okay. How about others?
Sir, I believe Sanket he rejoined.
Yeah, Sanket, are you there?
Yes, sir.
Have you watched the videos of this week
Yes, sir.
7?
Yes, sir.
Fully? Then you can
Yes, sir.
ask questions. You can start asking questions right away.
Yes, sir.
At least for the first slide, you can ask any question. If you will start slowly. So in this, if you have a sinusoidal input A sin omega t, you'll have output B sin omega t plus phi. The gain is B by A is called the gain, and the phi is called the phase shift. Both depend on omega, and they depend on frequency. And how the gain and the phase depend on frequency of the input, it's purely depend on the transfer function of the system. So, any questions on this part?
No, sir. The Nyquist criteria of stability, sir.
Want to straight away go there?
Or sir, maybe what we can do is instead of skipping through it, maybe you could like really quickly in 10 minutes cover all three lectures. Just cover the important topics.
Okay.
Yes, sir.
Now, the advantage of frequency response plot is it can directly be used for design. With even if you don't know the transfer function, you can supply various frequencies, get the output, and then plot the magnitude and gain. Plot the gain and phase shift, and then you can plot them, and then we can directly use that for your analysis. You don't need to model the system from scratch. Okay, even if you have a raw frequency response data also, you can manage with that. Okay, so you don't need to explicitly mathematically model and then derive the transfer function and do all that work. Okay, so the thing is, how to obtain the frequency response is put S equal to j omega. Whenever you have a transfer function, what you do is when you put S equal to j omega, you will get the frequency response function. So find the magnitude of the complex number and the phase of the complex number. When you put S equal to j omega in a transfer function, you'll end up with a complex number, right? And that complex number will have magnitude and phase, and that is what is the magnitude and phase shift. So again, so if you plot the frequency response, let's say for a second order transfer function, then you will get something like this magnitude response. So you see the magnitude response peaks at the resonant frequency. It starts with 0 and then peaks at the resonant frequency and then falls off. So in frequency response, one very important thing to notice, you're plotting everything in a log scale. The frequency axis is plotted in 10 power, log scale. So this is 10 power 0, this is 10 power 1, 10 power 2. All the 0, 1, 2, you see other powers in 10. So similarly, the magnitude response that you see is actually decibels, 20 log. Okay, so when the gain is 1, log 1 is 0, right? So when you are having 0 decibel, which means the gain is actually 1. And anything above 0 decibel means the gain is more than 1 amplification. Anything below 0 means gain is less than 1 and it is, shrinking. So for this, and the lesser the damping, more the peak, resonant peak will be, okay. So if we have this transfer function, this is the channel transfer function we saw, right? You remember this? Correct? So here when you
Yes.
put s
Yes.
equal to j omega, you will get minus omega square here, and then plus j2 zeta omega and omega plus omega n square. And then if you simplify that, you will take only the magnitude response and then plot that, you will get this. So as I said, when the damping ratio reduces, the resonant peak actually, increases. When damping is equal to 0, then the resonant peak will be infinity. Okay, so at omega equal to omega n, you will have infinite response. Okay. Now, of course, theoretically, there cannot be perfectly damping, cannot be 0 perfectly. So there will always be some minute damping, so it will not be infinity, but a very large finite number. but this is just a limiting case. And this is the phase response that you see. So what you see is as zeta is becoming smaller and smaller, the phase plot kind of becomes sharper. It is zero and then suddenly goes to 180, drops to minus 180. When zeta is not that low, it kind of slowly drops from 0 to minus 180 gradually. But as zeta decreases, there's a sharper change, until omega less than omega n, you don't fall very close to 0, but slightly bigger than omega n, you will kind of jump to minus 180. There's another thing that you see, the phase plot. And like in the step response, you have three parameters for second order system, right? Like that for frequency response, you have three parameter design. One is the resonant peak, the other is the resonant frequency, and the other is the band. So resonant peak is basically the magnitude of this guy, whatever you see here, the peak value that you see here. And then the resonant frequency is where this peak occurs in frequency. Okay? That is called the resonant frequency. So the bandwidth is basically how much the system, it's a measure of, uh, it again depends on various things, but it's a tolerance, it depends on the tolerance that you take. So it's a measure of at what frequencies the system response is very sensitive, at what frequency range. Okay. So these are the formulas for the resonant peak and the resonant frequency and the bandwidth. If you work it out, you will get it. And the thing is, this is time domain specification and frequency domain specification. They are reconnected together here. So in time domain, if you lower the theta, it results in higher oscillation. In the frequency domain, if you lower the zeta, it leads to sharper resonance peak. Instead of overshoot, you'll have a resonant peak here. And then a high zeta flattens the response, in frequency domain, whereas here it results in a smoother and slower response. Up to this, any questions? Any questions till here?
No, sir.
Okay, then let me go to week 2. So week 2, so far we have plotted the magnitude and phase separately as functions of frequency, correct? X-axis we have the frequency in decibel scale. Sorry, x-axis we have frequency in log scale, and the y-axis we have either phase in degrees or magnitude response in decibels. Whereas in polar plot, what you do is when you put s equal to j omega, you get a complex number, right? Correct? You remember? So at various frequencies, you get a complex number, right? You directly plot that complex number in the complex plane, okay? So you trace that complex number in the plane at various frequencies, and then you see how the trajectory evolves. Okay, how that point, which point in the complex plane that includes the magnitude and the frequency moves as omega moves. That is called the polar plot. So in polar plot, the magnitude information and the phase information are simultaneously visible. Whereas in the body plot, you have to extract it separately from two different graphs. Whereas here, what you do is you allow frequency to run as a parametric running variable, and then for various frequencies, you kind of see how the point in the complex plane that represents g of j omega travels as omega increases from 0 to infinity. So that is what is the polar plot of the system. So, for example, here take this transfer function 1 by 1 plus st. When you put s equal to j omega, you get 1 by 1 plus j omega t, right? Assume t is 1 just for simplicity. So you'll get 1 by 1 plus j omega, right?
Yes, sir.
Correct? At omega equal to 0, what is happening? Put omega equal to 0, what is m, what is phi? Yeah, 1 by 1 plus j omega. Put omega equal to 0, what do you get? The number 1, just 1, right?
1.
1 plus
Yeah.
0 j. So that is here. You see this? That will be the right hand side here. You see here? The magnitude
Yes,
is
sir.
1, the angle is 0 degree, 1 plus j 0. Correct? As omega increases, what happens is the phase gradually, reduces, and then the magnitude also gradually reduces. So in complex plane, magnitude is nothing but the radius, right? Distance from the origin, radius, right? Correct? So magnitude
Yes,
reducing
sir.
actually means the circle becomes smaller and smaller. It goes through smaller and smaller circles about the origin, and the phase becomes minus 90 degree. Correct. So it will touch the origin, uh, tangential to the minus 90 degree line, which is same as plus 270. Plus 270 is same as minus 90. So the polar plot will touch the origin asymptotically at omega equal to infinity, tangential to the minus 90 degree axis. Do you get this plot? Got it?
Yes, sir.
Yes, sir.
Now let's do for a second order system. In second order system, you have two time constants. Assume that's real poles, both are the real poles, not complex conjugate. So you put s equal to j omega, you get 1 by 1 plus j omega t1 into 1 plus j omega t2. Again, when omega equal to 0, you start at the same point here. But as omega increases, so what happens is the
Possible
system
to
has,
annotate.
yeah, yeah,
So,
please.
is it possible for you to annotate so that we'll have some visual memory after this?
Annotate means highlight or something.
Like if you have a writing pad attached, then maybe whatever you're saying, you can also like just write that part because the
The
first order
meeting
was
is recorded, right? Anyway,
yes, yes, yes.
I don't have any pad. I'm just sharing from a laptop, not an iPad or something. So,
I see. Okay, okay.
okay, do you want me to open in a MATLAB and show live script?
Um.
That will be
Uh.
better, right?
No, I think that's fine then. I was just saying if you could like write it down, 1/1 plus j omega t1 plus, and then when we take the what do you say, the magnitude.
Okay, what I can do is I'll try my best. Just a moment.
I mean, only if it's possible. Otherwise, it's fine.
Yeah, just give me some moment. I'll try to think of something. Yeah, because the steps are not worked out here. That's why you want it. I'm getting it. I'll open a Word document and I type whatever I can, okay?
Sure, that will work.
Polar plot is very important for Nyquist criterion, so I'll go a little bit slowly here. Yeah, I think I got ready. Let's see how it works. What happened again? My screen visible?
Yes, sir.
Yes, sir.
Yes.
Yeah. I'll work it out step by step here. Let me increase the font size. So when you have g of s is 1 by 1 plus, let's say, s plus 1. Is it fine?
Yes.
So now what will be g of j omega?
1
1
by
by
1 plus j omega.
j
1
omega
plus j
plus
omega.
1. So what is the magnitude of this?
1 by under the root 1 plus omega square.
Yeah.
Under the
So
root
1
omega.
by root of, and what will be the phase?
Minus of tan inverse 1 by omega.
Tan inverse of 1
Omega
by,
by 1. Omega, sir.
sorry. So you see what is happening here is the magnitude kind of falls. It starts with 1, right, at omega equal to 0. And then it falls to 0 gradually, right? You see, look at this function, correct? At omega equal to 0, it is 1, and gradually at omega increases to infinity, it falls off to 0,
Decreases.
right? Whereas this guy, what happens?
This will be tends to minus 90.
When omega equal to 0 means initially the tan inverse 0 is 0. But as omega tends to infinity, it becomes tan inverse infinity, which is 90. Minus of that is minus 90, right? So
Yes.
that's what is happening here. Got it? So so here the magnitude is shown by circles. The radius of the circle, distance from the origin is magnitude, right? For a complex number, correct? Which is the radius of the circle from the origin, right? Got it? So as
Yes,
omega
sir.
increases, it goes into smaller and smaller circle. Eventually, it touches the origin tangentially to minus 90 degree line. So 270-degree line vertically 270 degrees, same as minus 90. It touches tangentially to that. Got it? Got it?
Yes, sir.
Now let's do it for a second order system like this. So I'll take a very simple concrete example. Let's say 1 by s plus 1 into s plus 2. So what is again g of j omega?
1 by j omega plus 1. J omega plus 2.
And what is the phase?
Minus tan inverse omega and minus tan inverse omega by 2.
So again, what you see here is again the magnitude plot is again 1 by square root of 1 plus omega square into 4 plus omega square, right? The
Yes,
entire
sir.
thing, correct? So again, if you see the magnitude reduces to 0 as omega increases, correct? But what is the phase now? Asymptotically, where does it go as omega becomes infinite? It
Minus
becomes
80.
2
Minus
minus 90
180.
minus 90 minus 180, right?
Yes, sir.
So that's what is happening here. It touches origin tangentially to the minus 180-degree line. You see here?
Yes, sir.
Got it?
Yes, sir.
This is for pole at the origin. 1 by s into 1 plus s t1. So let me call that. Let me take t equal to 1. So you'll have 1 by s into s plus 1. That's for simplicity. Got it? So again, when you put s equal to j omega, you get 1 by j omega into j omega plus 1. So what is the magnitude?
1 by omega square
1 by omega into
on
1 by omega
under the
log
root.
omega. Okay, 1 by omega times. Correct?
Yes, sir.
What is P? Phase. Minus arc tan inverse of omega by 0,
Omega
right?
by 0. Yes, sir.
And then
Minus
minus A tan of.
tan inverse omega. Omega.
But what is A tan of omega by 0?
It's 90 degree. Minus 90.
Yeah, minus 90 minus. So what do you think is happening here? When omega equal to 0, what is the magnitude?
Magnitude will be 1.
Hello, put omega equal to 0 here.
Oh, sir. Infinite.
Yeah. And what is the phase when omega equal to 0? This will be 0, right? What is
Yes,
the
sir.
phase? Minus 90 degree,
Minus
right?
90. Yes, sir.
So this plot, it starts when omega equal to 0. It's actually infinite, but it is parallel to the minus 90 degree line. Got it?
Yes, sir. Yes, sir.
Uh, so you'll have something like this. As omega increases, the magnitude, what does it happen? As omega tends to infinity, what is happening here?
The magnitude tends to 0.
Yeah, it tends to 0. So the same thing. It touches the origin with parallel to minus 180 degree, right? But the thing is, it starts at minus 90. Got it?
Yes, sir.
So that is what it's shown here. Got it? In fact, if you expand this, you see, you can actually simplify this. What will happen here? 1 by what is j omega into j omega?
Minus omega.
Minus omega
Minus
squared
omega. Yes, sir.
plus j omega, right? 1 by j omega minus omega square, right? So if you take the conjugation, what will happen? You know to perform conjugation, right? Make the denominator real. And what will happen then? Multiply and divide by minus omega square minus j omega. What will happen? You'll get
Minus omega square minus plus omega square.
by by what is the complex number into its own conjugate?
It is omega to the power 4 minus omega square
Plus, right?
divided.
Oh, wait a minute. So what is the real part of this? You have something like this, right? Now, can I cancel stuff here in the real part? Well, I can cancel omega square, right? Correct? Got it?
Yes, sir.
Fine.
Yes, sir.
So when omega equal to 0, what's the real part? Put omega equal to 0, what's the real part?
-1.
-1.
So that is why the plot starts at -1. This point is actually -1. Okay, the green color where it touches the x-axis is actually -1. The real part is starting at -1, but the imaginary part is infinite. Okay, so if the real part is -1 and the magnitude is infinite, then the imaginary part has to be infinite, right? So that's why it starts like this. Do you get why?
Yes, sir.
Others? See, you should get comfortable with polar plot as comfortably or with the Nyquist plot. Have you done Nyquist plot for amplifiers and all before?
No, sir.
No, okay, then this is new. Okay, so pay attention and ask a lot of questions. Okay, Bode plot you must have done for amplifiers and all, right?
Very briefly, to say the least.
Okay, so then pay attention here. Okay, ask many questions as you can. So this plot is clear. So here the actual frequency is not visible. Frequency is a running parameter here. Okay. Like when I draw
Yes,
the
sir.
trajectory traced by a person, the time is not visible, right? It's just a running parameter, right? As time progresses, wherever that point is running, I just trace it. So time is a running parameter. That likewise here, the frequency is not explicitly shown. It's a running parameter. Starts from zero, ends to infinity. Okay, but it's not explicitly shown here. Only the magnitude and phases are shown at once together. Okay. Now let's go for third order system. Okay. Again, you have three poles now. Okay. So if you have three poles, let me do the math here. Call them, let's say S, S plus 1, S plus 2. So what is G of J omega?
1 by j omega. 1 j omega plus 2.
So I can calculate the phase very quickly. What is this phase response?
-90 minus omega
Let
minus
me go
omega by
step by
2.
step for now. So the phase starts at -90. If you simplify this, so it starts at -90, ends where? At omega equal to infinity, what happens? What is P of infinity?
So it goes to -270. It means -90.
So for a first order system, the asymptotic phase is -90, right? For second order, where did it go? -180. Do you remember?
Yes, sir.
Third order is going. So if
Minus
you
270.
look at, you can see here actually first order, the phase is going to -90, right? As omega equal to infinity. This is for the first order case. Got it?
Yes, sir.
For second order, what happens is you have two arctans, and hence when omega equal infinity, it goes to -180. Okay, of course, when one of the poles at the origin, it starts at -90, but doesn't matter whether it starts at 0 or starts at -90. Eventually, it goes to -180 if the order is 2. But if the order is 3, here it starts at -90 because one of the poles at the origin. But value tends up is always minus 270. So you can always see a pattern here. So for order n, what can you guess? What is the formula for nth order system with n poles and no zeros? What will the asymptotic phase be? Guess no.
Minus 90 into n.
Minus 90
Into n.
n. That's it. So here you have the third order. It's minus 270. It's same as plus 90, right? Again, it starts at minus 90 because for the same reason why this guy starts at minus 90, because there is a pole at the origin. If there is one pole at the origin, it starts at if there is no pole at the origin, it starts at 0 degree. So again, let me ask you to guess. If there is no pole at the origin, then the phase starts at 0. If there is one pole at the origin, the phase starts at minus 90. If there are two poles at the origin and no zeros, where will the phase start? Any guess?
Minus 180.
Yeah. And similarly for n poles at the origin, P of 0 will be
Minus 90. Yeah.
so now let's see this. Sorry, I think it's around. Yeah. So you understand this plot now, it starts at minus 90 because there is one pole at the origin. For the same reason, the real part is minus 1. And then it asymptotically ends up at plus 90, which is minus 270. Got it? Got it? Hello.
Yes.
So
Yes,
this
sir.
is type 1 and order 3. Now let's go to stability. Again, stability depends on the where the roots of the characteristic equation in the closed loop are. Again, if you want to plot the polar plot of the system, you can go to MATLAB. Here I'm using a free version of MATLAB called Octave. So I think the command is polar or sys or something. Let me try here. So numerator transformation, let's call it 1. Denominator, let's call it 1, 1, which is s plus 1. So let me call the transfer function. See here? And then let me plot the polar of sys. Wait, I think I typed the wrong command here. Just a moment, I'll see what the correct command is. I think we should use Nyquist of sys. Yeah, this will work. Similarly, if you type Bode of sys, you will get the Bode plot. Okay. If you type R locus of sys, you will get the root locus. Are you familiar with this? Are you familiar with these commands?
Yes.
Yes, sir.
Okay. I don't need to go there. Okay, let me start with stability in the frequency domain. Now let's consider a complex function which has zeros, m zeros at alpha 1, alpha 2, alpha m, and n poles at beta 1, beta 2, beta n. Okay. Now, this is a complex function, right? When you input a complex number s, it outputs another complex number which is q of s, correct? Got it? This is correct, right?
Sir,
Like
can you repeat?
when you have real numbers, f of x equal to x square, it's a real function, right? When you put x, it outputs f of x which is x square, right? To visualize a real function, you just need a graph sheet. You know, one axis is x, and the other axis is f of x. Whereas for a complex function, things get tricky because s itself requires two axes, complex numbers, and q of s requires another two. You need total 4 dimensions to visualize, which is not possible. So that's why we have to look for another shortcuts. Okay, that is what we are going to do now. So now what you can ask is this basically: when I travel a loop in the S-plane. Let's say somebody travels in the S-plane in this path. Got it? I can ask, what will the corresponding image in the Q of S-plane travel? It's a very valid question to ask, right? Q is a function that takes you one complex number to another complex number. So if each complex number can be represented in the complex plane. So if some guy travels in this loop in the S plane, I can ask where will it get mapped to in the corresponding Q of S plane. You may get something like this. Correct? Are you understanding what this plot means? Are you understanding what this plot means? I can't directly plot complex functions together. I need 4 dimensions for that. So I will choose particular paths in the S plane, and then I'll plot their corresponding mapping into the Q of S plane. Is this clear or not?
Yes, sir.
See, you have to tell me that otherwise I'll explain again. Nothing shy about that. Now, we are not exactly interested in the exact shape of the contour. We are interested in detecting poles, right? Whether there are poles in the right of the complex plane. Okay. Now, let's ask this question. Let's say you have a point S in the S plane. Okay. You see the diagram here? I'll zoom. This is a very important diagram. I'll charge my laptop. Just a moment. Are you able to see this diagram?
Yes, sir.
So here I think, what was the notation? Alphas are the zeros, betas are the poles. Okay, see here. Alphas are the zeros, betas are the poles. See very carefully here. So the rounds are zeros and the crosses are the poles. Okay.
Yes, sir.
So you take an arbitrary point, yes. Now, let's say, yes, yeah, somebody circles around alpha 1, makes a loop around alpha 1, okay? But doesn't encircle beta 1 or beta 2 or other alphas. Okay, now, what will happen to Q of S? Remember, Q of S has S minus alpha 1 here, correct? So when S encircles alpha 1, Q of S will encircle the origin, right? Correct? See, look at this. Are you able to see my mouse?
Yes, sir.
Yes.
So as this entire thing is S minus alpha. This entire arrow is S minus alpha. Do you see here?
Yes, sir.
Now, as S moves around like this, in this closed loop, S minus alpha, this part connecting alpha 1 to S, which is S minus alpha, it completes a full circuit around alpha. You see? Correct?
Yes, sir.
Now, so Q of S will complete a full circuit around the origin, correct? Because Q of S has S minus alpha here. So as S encircles alpha, S minus alpha encircles the origin, correct? If this is going right side, this will also go right side because this is 0. Correct? Are you able to understand this or
Sir.
not? Yeah.
Sir, on this line on the left graph, this is S minus alpha or alpha minus S? Because alpha is above that point.
S minus alpha, right? That arrow.
So
Final
won't it
minus
be
initial,
alpha
right?
minus
Final
S?
minus initial, right? The arrow, final minus initial is the vector, right? Okay, whatever you call S minus alpha, alpha minus S, you see that and as the point loops around alpha, right, clockwise once, Q of S loops around the origin clockwise once. Do you see that, right?
Yes.
That much you are able to see, right?
Yes.
Whereas for other poles, beta 1, beta 2 or other zeros, as S loops around, S minus beta, these guys, they only oscillate, they don't complete a full circuit if you visualize. As they go around, they just they just swing mildly, but they don't complete a full circuit. Do you see? So whatever happens here, these guys, they don't complete the full circuit around the origin, these guys. Only this part makes the Q of S complete the full circuit around the origin. Since it's a 0, it is completing the same direction as clockwise. This is also clockwise. Do you get this? It's actually very simple once you understand it. Initially, it is kind of tough. Now, similarly, if the S-plane contour encloses two zeros, okay, there are two zeros here, alpha 1, alpha 2, both are inside. This will complete two loops around the origin. One due to S minus alpha 1, another due to S minus alpha 2. Assume the zeros are alpha 1, alpha 2, both are inside. Okay. If the contour does not encircle any pole or zero, then the Q of S contour also will not encircle the origin at all. So assume your, the loop is like this. Assume the loop is like this. Then this loop will be also something like this. It won't encircle the origin. Got it? The fundamental premise is this. Q of S has a bunch of S minus alphas and S minus betas. So as S minus alphas complete full circuits, as S completes full circuits around alpha, the S minus alphas complete full circuit around the origin, because putting S equal to alpha makes it the origin in the Q of S plane, right? When you put S equal to alpha, what happens? Q of S becomes 0, it becomes the origin, right? So the point alpha gets mapped to the origin under the S minus alpha, correct? So any encirclements about alpha in S plane will translate to encirclements around origin in the Q of S plane because of the displacement by alpha.
Yes,
Now
sir.
if the contour encircles a pole, it will be the same thing except that the arrows will be reversed. If you have a clockwise encirclement of a pole, you'll have an anti-clockwise encirclement of about the origin in the Q of S plane. because it's a reciprocal, right? In the reciprocal, the phase reverses. So clockwise becomes anti-clockwise, correct? The phase of one by a complex, the phase of a reciprocal of a complex number is negative of the, phase of the original complex number, correct?
Yes, sir.
So if there are p poles and z zeros of q of s encircled by the S-plane contour, so the original S-plane contour loops around p poles and z zeros, then the net encirclement of the origin in the counterclockwise direction is p minus z, correct? Because each pole contributes an anti-clockwise encirclement. Assume that this origin contour, S-plane contour is always clockwise. Then if you have a zero, it contributes clockwise encirclement. If you have a pole, it contributes an anti-clockwise encirclement. So the each pole adds an anti-clockwise encirclement and each zero adds a clockwise encirclement. So the number of counterclockwise encirclements is equal to P minus Z, where P is the number of poles and Z is the number of zeros inside the contour. Okay, outside doesn't matter. Correct?
Yes, sir.
For example, here, this for this diagram here, beta 1, beta 2 don't matter because they are not inside the contour. This contour doesn't encircle them. Betas, it encircles only alpha 1. So here P is 0 and Z is 1. So the number of counterclockwise encirclement is 0 minus 1, which is minus 1. So saying counterclockwise is minus 1 is same as saying clockwise is plus 1. Okay. Counterclockwise encirclement as a negative of a clockwise encirclement. This is a very important theorem in complex analysis. The number of encirclements about the origin, counterclockwise encirclements about the origin for a Q of S contour is P minus Z, where P and Z are the number of poles, the number of zeros encircled by the S-plane contour. Okay. This is the many basic criterion for Nyquist plot. Got it? Now, what happens here is in Nyquist plot, if you have Q of S like this, I will go to Word document again. Can you see the Word document? Can you see
Yes,
the
sir.
Word document? So let's
Yes, sir.
call Q of S, numerator of Q. Let's Q of S be the transfer function. Okay, open loop transfer function. Okay. So this is an open loop transfer function. Got it? So let's numerator be n of s and denominator be d of s. So what is the closed loop transfer function now? G by 1 plus g, right? Correct?
Yes, sir. Yes, sir.
So the poles of the closed loop transfer function are nothing but the
The pole
zeros,
of G of S.
zeros of 1 plus g. But what is 1 plus g? 1 plus n by d, which is correct? 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 Hello.
Yes.
See, this is a very important point. That's why I'm asking again and again. Okay, wait. So now, see here. So this is d plus n by d. Okay, this is uh, 0 sub 1 plus g. So now what it is being said here is the zeros of q plus s are nothing but the roots of the characteristic equation, and the poles are same as the open loop poles. Okay, let me explain this with an example. Any example here? Okay, not much. Let this is g of s h of s. Okay, so this is nothing but the open loop transfer function. Okay, it has m zeros and n poles. Got it? Q of s is 1 plus gh, correct? The zeros of Q of s are the poles of the closed loop. You agree or not? Do you agree? Because the closed loop transfer function is g by 1 plus g or g by 1 plus gh when you have a h. So the poles of the closed loop transfer function are nothing but the zeros of 1 plus gh, which is defined as q here. Okay, sorry, this is not q. Is this fine here? What I'm
Yes.
saying is the zeros of q of s are the closed loop transfer function poles. Got it?
Yes, sir.
What are the poles of q of s? Now let's see what are the poles of q of s. So 1 plus gh is q, right? Assume gh is some numerator by denominator. So the poles of q of s are nothing but the poles of 1 plus gh, which is the poles of 1 plus n by d, which is d plus n by d. So what is the pole of this polynomial? So what is the pole of this d plus n by d? Is nothing but the zero
The zeros of P.
of
Okay.
d, right? Correct, because
Yes,
denominator
sir.
has to
Yes,
be
sir.
zero for the pole, right?
Yes, sir.
But what are the zeros of d? They are the open loop poles, right? These are the open loop poles. When you put d, so you see here, these are open loop poles. Accept it. So the important point is the zeros of Q of S, nothing but closed loop poles. Whereas the poles of Q of S are nothing but open loop. Got it? Is this clear or not? Is this clear or not? Hello, I'll ask one by one. Dhruv, is this clear?
Yes, sir.
Namai?
Yes, sir. Clear.
Manisha?
Yes, sir.
So this is a very important point. That's what they are saying here also. So the zeros of Q of S are the roots of the characteristic equation, which is the closed loop poles. Whereas the poles of the Q of S are same as the open loop poles. Got it? Now, for stability, what we want is the zeros of Q of S, all of them have to be in the left half of the complex plane, correct?
Yes, sir.
Or another way of saying it is the zeros of Q of S should not be in the right half of the complex plane. Got it? Got it?
Sir.
Got it or not?
Yes, sir. Got it.
Okay. Now let's see where the logic takes us. Now what I do is I take a contour, okay. Take a semicircle contour like this, okay. You go start from this point. Do you see my cursor? Do you see my cursor here?
Yes, sir.
Start here, go and then stop here and then take a loop here. Imagine a very big clockwise semicircle. Center origin, radius r, okay. Imagine this. Got this? Imagine
Yes,
a
sir.
big clockwise semicircle, center at origin of radius r. As r tends to infinity, what happens? The circle, semicircle grows bigger and bigger, right?
Yes, sir.
So do you agree that as r tends to infinity, this gigantic clockwise contour
Will be right hand.
encloses all the
Right
right
hand.
of plane, correct?
Yes, sir.
Do you agree? It's a trick, it's just a mathematical trick, nothing more. So such a contour is called Nyquist contour, okay? As r tends to infinity, this part will no longer be visible now. It will all be go to infinity. You'll get just this part, the entire imaginary axis. Got it? So as r tends to infinity, what happens is this semicircle is made up of two parts. One is the diametric line, straight line. The other part is the curve here, circular thing, right? But as r tends to infinity, this straight line will enclose all of the imaginary axis, correct?
Yes, sir.
And this part will become invisible. This will go to infinity. This curvy part will go to infinity and the straight part will enclose all of the imaginary axis, correct? Got it? Got it? So I choose this is my S-plane contour. Okay, so I choose as my S-plane contour a gigantic semicircle, clockwise semicircle, enclosing the entire right half plane. So now what will be the number of counterclockwise encirclements about the origin in the Q of S plane? What will this be? It will be P minus Z, right? Number of poles of Q of S in the right half plane minus the number of zeros of Q of S in the right half plane, correct? Do you agree? This we already saw here previously. Taken a S-plane plot, the number of counterclockwise encirclements is P minus Z, the number of poles and number of zeros inside, that is inside the contour, okay? But our contour encloses all the right half planes. So the number of counterclockwise encirclement of Q of S about the origin is equal to number of poles of Q of S inside that contour. But this contour is an entire right half plane, right? So the number of poles of Q of S on the right half plane minus number of zeros of Q of S on the entire right half plane. But what are the poles of Q of S? That's no we saw. What are the poles of Q of S? The poles of Q of S are the open loop poles, correct? And the zeros of Q of S are the closed loop poles. So this entire formula will now be reduced to number of Unstable. Right afferent poles are unstable, right? Unstable. Non-stable. What are the poles of QFS? Open loop poles. Minus the number of unstable
Zeros.
closed loop poles. Got it? So let's call this number of encirclements n. So now we have to go further again. Little bit more work is required for deriving the criterion. Now, number of encirclements. So again, remember Q nothing but 1 plus GH. The number of encirclements of Q, which is 1 plus GH, about the origin is equal to the number of encirclements of GH, just GH, about the point minus 1 plus J0. Do you agree with this? You add 1 to GH to get Q. Correct? So, counting the number of encirclements of this big guy about the origin is same as counting the number of encirclements of just this guy about the point minus 1, right? Because 1 is nothing but 1 plus J0 in the complex plane, correct? Correct? Any encirclement of GH about minus 1 plus J0 will contribute the encirclement about the origin here, right? Got it?
Yes.
But when you do this entire contour, if you see, as r tends to infinity, is nothing but the imaginary axis, the entire imaginary axis. This part goes to an infinity. So this is nothing but the Nyquist plot, okay? This is just a Nyquist plot with a mirror image. Normally Nyquist plot will be omega equal to 0 to infinity, right? This part. Now you are also including omega 0 to minus infinity. This part also you are including. So this will just be the Nyquist plot and the mirror image together. So the Nyquist plot is nothing but the polar plot plus the negative frequency part. In polar plot, I include only the positive frequency part. In Nyquist plot, I also include the negative frequency part because I want to map this entire contour. So what you have here is, again, Nyquist plot of GH. Nothing but polar plot of GH plus the negative frequency included. So the number of encirclements of the Nyquist plot about the point minus 1 plus J0 is counterclockwise. Is nothing but you have derived down is equal to what? Number of unstable open loop poles minus the number of unstable closed loop poles. Now here there are three quantities here. This number of unstable open loop poles, you know already. Open loop system, you know, what are the poles, and you can calculate how many of them are unstable. This, you can draw the polar plot and the negative frequency plot, which is called the Nyquist plot, and then this we can find out. This is the only unknown variable that was mysterious. This, hence you can find out this. Correct? 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 Now assume the open loop system is stable. Assume the open loop system is stable just for a moment. Then number of unstable open loop poles is 0, right? So what is the condition for stability? For stability, this yellow part has to be 0. So for stability, the number of counterclockwise encirclements of the Nyquist plot of GH about the point -1 plus J0 should be 0 if the open loop system is stable. So if the closed loop system, if the open loop system is already stable, and you also want the closed loop system to be stable, then the Nyquist plot should never encircle -1 plus J0. If it does, you are gone. If it does, the number of such unstable closed loop poles is given by the number of minus the number of counterclockwise or the number of clockwise. So that is what is the Nyquist stability theorem. So what it says is basically this. N is the number of clockwise encirclement. So number of clockwise is negative of counterclockwise. Okay. So you can simplify this. Okay. Here, if you change this counterclockwise to clockwise and then bring this negative to plus, what you get basically is this. The number of unstable closed loop poles that you want to find is this. Is basically number of unstable open loop poles, which is this, right? Minus the number of counterclockwise encirclements of the Nyquist plot about -1 plus J0. If you know the open loop system is already stable, then this part will be 0. And hence, the number of unstable closed loop poles is equal to the number of clockwise, because negative will become positive, right? When you change direction. Equal number of clockwise encirclements of the Nyquist plot about -1 plus
-1.
J0. The open loop system is known to be stable. These two are the important statements. The first is a very generic statement. You can derive all the other things from here. That is what is summarized here. So for stability, what you want? Or another way of putting this should be, if you want stability, which means this guy has to be 0, the yellow guy has to be 0, then what should happen? The number of unstable open loop poles should be what? Equal to the number of counterclockwise encirclements of the Nyquist plot
Minus.
about minus
Minus
0.
1.
This is the condition for stability. This is the stability criterion. So that is what is the various cases of that are summarized here. Z is the zeros of Q of S, which is the closed loop poles, and P is the number of open loop poles are all unstable. Okay. Up to this, it's clear.
Sir, can you?
Very important. It will sound very complex, but it's actually very simple once you get the idea. Initially, it will be all very crazy, but yeah. Any questions? I'll stop here for a few minutes, please. If you have the slides with you, go through it again. Try to make sense out of it. Ask me. Because it's a very important topic. I will teach you how to draw Nyquist plots and check after you let me know. For now, understand this result. What a Nyquist plot is and how is it important in determining stability. So the Nyquist plot is nothing but the polar plot plus the negative frequency part included, which is the mirror image. So when you put S equal to j omega, you get the polar plot. When you put S equal to minus j omega as well and plot that also, together you show S equal to j omega and S equal to minus j omega, you get the Nyquist plot, okay? So you take the mirror image about the horizontal axis, you get the Nyquist plot because replacing j omega by minus j omega is basically imaginary part negativization, which is reflection about the mirror placed horizontally, correct? That we'll see later, but for now, see if this makes sense. So for stability, the amount of encirclement, the number of counterclockwise encirclement about -1 plus j0 for the open loop Nyquist plot of the open loop should be equal to the number of right half plane unstable open loop poles. That is what I have written here as well. The number of counterclockwise encirclement of the Nyquist plot about this -1 should be equal to the number of unstable open loop poles. If the system has no unstable open loop poles, then there should be no encirclement at all. I'll wait for 5 minutes and then we'll continue. If you have the slides with you, side by side or any notes, go through it and a very important topic, so try to make sense out of it again. Okay, shall we start again? Sanket? Others have gone. How many are
Yes,
there
sir.
now?
Yes, sir.
Any questions so far?
Sir, can you take an example?
Yeah, that I will do. For now, any question? So let's take an example here. This example, second order system. So far we saw this part. The bottom part was what already we saw, right? Polar plot. Correct?
Yes, sir.
Now take the mirror image of that about the horizontal axis and complete it. You will get a full loop. This is a Nyquist plot. Got it?
Yes, sir.
Now this Nyquist plot, it doesn't encircle the point minus one because the point minus one will be somewhere over here, which it doesn't
Yes, sir.
encircle, right? And this system is already stable. The number of open loop poles are zero. Unstable open loop poles are zero. So the encirclements are also zero. So the closed loop system is stable. Okay. Hmm? Got it?
Yes, sir.
Take for this system. So for this system, you see, the system has an unstable pole here, correct?
Yes, sir. S is equal to 1.
And this is the Nyquist plot here. And what is the number of times? What is the number of counterclockwise encirclement about the origin? About minus one. This point is minus one, shown in red inside. What is the number of counterclockwise encirclement about minus one?
1, sir.
One. It's not minus one, it's one because it's also counterclockwise. So the number of counterclockwise encirclement here, this guy, about minus one is equal to the number of unstable open loop poles because there was one unstable open loop pole. Corresponding to that, there is a one counterclockwise encirclement about minus one, right? So it is stable, correct? Correct?
Yes, sir.
This is also stable. See, now we are showing special cases. Now take this. For here, this part we got here, right? We got this part in the polar plot. Do you remember?
Yes, sir. Wow.
Take the mirror image, you complete the full Nyquist plot.
Yes, sir.
And then you complete it clockwise, you will get the full Nyquist plot around infinity. This point is invisible. So here again you see the number of counterclockwise encirclement about minus one is zero because minus one will be here somewhere over here.
Yes, sir.
Correct. The only point here is when there are poles exactly on the imaginary axis, you have to slightly bypass them. Correct? Because the value becomes infinite, right? At pole. So to avoid that, you have to slightly bypass them. In the process of bypassing them, you are doing this part. This part is nothing but a part of this dotted line, which is at infinity, is a part of bypassing them. Okay.
Okay, sir. Yes, sir.
When you bypass them to the right, so that you can include the imaginary axis pole in the left half plane and not count it. Okay. Again, this is another example. There are two poles at the origin and one pole at somewhere at the left. So this is the polar plot, and the mirror image is the Nyquist plot. You get two encirclements here. So z is equal to minus one. So this is unstable because the Nyquist plot encircles minus one and the clockwise direction only once. That is here you have two poles. that are unstable. Okay. I think this. I think we can stop here for this class. It will be too much otherwise, I guess. What do you think?
Yes, sir.
Let me see if there are lighter topics. Bode plot, you know how to draw?
Yes, sir.
Okay, then
Figure
maybe we can
marshals.
stop here, and or I'll give you some time. I'll stay online. Take your PPT or whatever book that you are using or whatever. You go through it and then ask doubts. Study it once. You can ask doubt. I'll wait for a few more minutes. Or are you okay with this? Are you clear with this?
Sir, I didn't get the second special case, sir, where two
Okay,
zeros
special
are.
case, it's okay. We'll see that later. Do you get the normal case?
Yes, sir.
If you get the normal case, I think you can also play around with MATLAB. If your Nyquist plot is basically for polar plot with a mirror image, right? So, one second. You have been taught MATLAB, how to use transfer functions in MATLAB.
Yes, sir. In DSP, we will use.
Let's take s plus 1 into s plus 2. So it will be s square plus 3s plus 2. And let's take transfer function. So this is a transfer function 1 by s square plus 3s plus 2. Then I'm doing Nyquist of this. You get this. So the dotted line is the negative frequency part. So here what you see is minus 1 is here, okay? In the Nyquist plot always the red part will be minus 1, okay? But the Nyquist plot is not exactly there at all whatsoever. If you can try a third order system, you may get something interesting. Okay, so here you see something.
Yes, sir.
So here, as we increase the gain, let me increase the gain. Instead of 1 in the numerator, I'll put, let's say, 10. And then I'll use the new numerator 10 now. If I increase the gain, and then plot the Nyquist, the plot will enlarge. If I increase the gain, it will be magnified. So now you see, it's a minus 1 is coming
Yes, sir.
inside that self-movement, right? So you see
Yes,
for
sir.
a third order case, if you increase the gain large enough, it goes unstable. It's the exact same thing you saw on the root locus as well. Do you remember the root locus? I
Yes,
plot
sir.
the root locus. You see, these three are the open loop poles. As you gain increases, you see it crosses the imaginary axis here. Do you see this? Here it crosses. You see here?
Yes, sir.
So what you conclude in the root locus, the same thing you have concluded in the Nyquist plot. And you can also plot the Bode plot, and you will. Okay. So you have to learn to compare between root locus, Bode, and Nyquist. Comparative analysis you have to do. because not all methods are perfect. They all easy in some situations. For example, root locus are very good for if you want stability, but root locus will tell you about closed loop poles, but they won't tell you about closed loop zeros. So you have to simulate the system to actually see whether it's performing as you expect or not. Okay, so lots of such subtle things are there. So in that case, Bode plot gives you the information about the zeros as well that you'll see in the Bode plot design. So you have to kind of start playing around yourself so that you are getting comfortable with uh, visualizing Nyquist, Bode, and root locus both intuitively and using MATLAB for precise design. Is this clear?
Yes, sir.
Okay, then we'll stop here, I guess, and then you can ask any question in the WhatsApp group or in the next time we meet. Okay.
Yes, sir. Thank you, sir.
Thank you.